talked about volumes of known cross-sections. When we talked about volumes of known cross-sections, we said that volume is equal to what? Do you guys remember what we talked about for volumes of known cross-sections? Volume is equal to the integral of area, right? So what we did, bless you, when we were doing volumes of known cross-sections is we found the area of that shape and then we integrated that, right? So like, for example, if we had a volume of a known cross-section and the cross-sections were squares, right, then we would be doing our base squared, and we'd be integrating from whatever to whatever of that base in terms of the functions given squared, right? And then dx or dy, depending on which way the perpendicular was drawn. Okay, you guys remember doing that? Okay, so with volumes of revolution, it works a little bit differently. Before we jump into the explanation, I know most of you watched the videos, and I talked about like the bones of the equation and that pi r out squared and r in squared stuff. I want to just give you a refresher on basic circles and area. Go ahead and draw this in your notes. Have a big circle, and the radius of that big circle is r out. Okay, the radius of the big circle is r out. Then, inside of that circle, I have a smaller circle, and the radius of that smaller circle is going to be called r in. Okay, so r out is like your outer radius, r in is your inner radius. If I wanted you to find the area of the big circle, what would be the area of the big circle? Knowing that the radius is called r out, what would be the area of the big circle? Yes? Pi r squared. So that area of the black circle would be pi r out squared. Right? Everybody okay with that? The area of the green circle would be what? Pi r in squared. So we would be doing pi r in squared. If I want to find, hi Sue.
I missed out. We're sorry to interrupt.
You're okay.
You have that to Lee.
Yeah, totally.
Thank you very much.
Of course.
Lee, Monday would be great if you could. You're the
Okay.
best. Thank you.
If we wanted to find the area between those, so I want to find the area of like the donut, right? I'm going to call it a donut. You're going to see it called a disc online a lot of times. What would be the area of this like red space here? What would that area be?
Pi r out squared minus pi r in.
Exactly. So it's the total area of the outer circle minus the total area of the inner circle. Does that make sense to everybody? Okay. Now, you could write this in a simplified way because you could factor out a pi. So the area of that donut, you might draw a little donut there. So the area of the donut would be pi parentheses r out squared minus r in squared. That would be the area of that donut. Is everybody okay with that idea? That's a super helpful place to start. What's nice about volumes of revolution is that it's always this equation. So when we're doing volumes of known cross-sections, you could have a square, you could have a triangle, you could have a rectangle whose base is 3 times its height. You could have a bunch of different shapes. When we're doing volumes of revolution, it's always a donut, or it's always a disc. Okay, so this is always the equation. That's why we're always going to integrate this equation. Okay. All right, let's jump into an example because I think we learn better from an example. We're just going to do setup but do not evaluate for all of these to make sure everybody can see how the setup works. Okay, so the question says, find the volume of the solid created when the region bounded by y equals x squared and y equals 2x is revolved about. And we're going to do 6 different variations. This is going to give us all of the different information we need for any volumes of revolution we encounter. Okay, this will work for everything. We're not going to actually integrate. Sometimes you are asked to integrate. We're just going to do setup. Okay, so let's first draw our picture. We have y equals x squared and y equals 2x. If we draw that picture, you're going to draw this picture like 6 times. So you're going to need a lot of room in your notebook just for drawing this picture because it's going to help how we draw our picture. So we have y equals x squared. That graph looks like this. And we have y equals 2x. That graph looks like this. I want to do 2x. Yeah, that's fine. Everybody okay with this? Okay, first thing we need to do anytime we're doing area or volume or cross sections or revolutions or anything like that is we need to find our intersection points when it says it's bounded by. So we need to find where this intersects. We're only going to find it on this first one because it's gonna be those same intersection points at least through C. We'll talk about why it might be different for the other ones. Okay, how do I find those intersection points as a review? Eric?
You set x squared and 2x equal to each other.
Yeah, we set our equations equal to each other. Don't cancel out the x or you're losing an answer. You should be factoring, so we're gonna subtract. So x squared minus 2x is equal to 0. You get x times x minus 2 equals 0. So your zeros happen at x equals 0 and x equals 2. This work is required, I wanna remind you, for free response, okay? And so make sure you always show this work. So we have x equals 0 and x equals 2, okay? Now, anytime, this is super important, anytime you see the word revolved or rotated, regardless of what else is happening, you're gonna set up what I'm gonna call the bones of your equation. You're not even gonna worry about anything else yet. You're gonna write the word volume, so not v equals, literally the word volume. You're gonna write a pi, an integral, and then a parentheses squared minus a parentheses squared. Every single time. When you see revolved or rotated, this is what you do. You start here every single time, okay? Now, sometimes you're gonna have a dx at the end, and sometimes you're gonna have a dy. You do need to think about that. You're gonna have a dx anytime you're rotating it this way. Anytime it gets rotated this way, okay? So that means around the x-axis or around a line like y equals something or y equals something. If you're rotating it this way, it's gonna be a dx. When would it be a dy? If you rotate it like this. So if you're rotating it this way, so around the y-axis or around x equals something, okay? You're never gonna rotate it any other way. So you're not gonna rotate it horizontally or around a different equation. You're only gonna rotate it either this way, which is the dx, or this way, which is the dy. That's it. Yes?
Why not?
That's all we do. That's it. For AP Calculus, that's all we do. We're only going to rotate it those ways. Okay, good question. All right, now, the thing that goes on our bounds is our intersection point. So that's going to be a 0 and a 2. The thing that's going to go in here is going to be your R out, and the thing that goes in here is going to be your R in. Let's talk about how you can easily find your R out and R in for any of these equations. This was a question I got a couple times over email, so I really want to make sure you guys understand how this part works, okay? I don't know if I said this in the video, so I want to really say it now and be clear. You always put your pen, marker, pencil, whatever you have, on the thing you're rotating it about first. So if I'm rotating about the x-axis, I put my marker on the x-axis. That's the first thing I do, okay? Then, to find R out, you're going to draw it to the furthest function away, not the furthest point away, okay? So I don't need to draw it to here necessarily. That might be the furthest point away. I just want to draw it to the furthest function. So the furthest function away from where I'm drawing is that 2x function. Does everybody see that? Okay? And I want to come up with what this distance is. Now this distance changes, right? Sometimes this distance is here, sometimes it's here. It's variable. It changes. So your R out should have a variable in it. Does that make sense? Okay, because your R out changes. So my R out is from the x-axis to this line, which is the equation 2x. That's how long this y distance is. Okay, so I'm going to write 2x. That's going to be my R out. To come up with R in, you put your marker, pen, pencil, whatever, on the thing you're rotating it about first. Every time the thing you're rotating it about first, and you draw to the closer function. Okay, and that distance to the closer function is your inner radius. Okay, so I have my inner radius is x squared. Again, I'm rotating it this way, right? Because I'm taking this thing and rotating it about the x-axis, so I get a dx at the end. Let me make sure we all understand how this works, why we're doing a donut, because maybe you're like, wait, why are we doing a donut? Where did that donut come from? Okay, so we have this area that we're rotating. This is the area that region bounded. I didn't even draw anything outside of that. Okay, on whenever I saw you, Monday, we talked about taking a slice. Right, we were saying like, take a slice out of this so we can imagine what's happening just with that one slice. Because what an integral does is it adds up all those slices. Okay, so what we're going to do is we're going to just imagine that one slice. We're going to forget about the rest of the graph. We're going to imagine if we rotated that one slice about the x-axis. Okay, so you can imagine, here's my slice, here's my x-axis, it's getting rotated like this. Okay, if you looked this way, what shape is that that's created? Not good at like moving this marker in the same way, but what does it create? Kind of creates a donut, right? So if you look at it like this, it looks like this, like taking that piece and rotating it, you're gonna have it essentially coming out of the board like this. But if you look at it through the axis like this, what happens is there's a donut shape there, okay? So all we're doing is we're adding up all of those donuts. So that's why we have that pi r out squared minus r in squared equation. That's always the equation anytime you're rotating or revolving, okay? And then you're just integrating that to add up all of those donuts. Are there any questions on that one so far? Any questions at all? Even if you think it's dumb, please ask. Any questions? Nothing? Okay, let's do it around a couple different places. So, we're gonna draw it again. So now we're gonna rotate around y equals -3. If we rotate it around y equals -3, we're gonna redraw. You only need to really draw this piece, but however you want. Like if you wanna keep drawing it bigger and keep drawing it like this, that's fine. You only need to draw the piece that's bounded, okay? Make sure you know which function is which, so I'm gonna use colors to distinguish. So this is my 2x equation, and this is my x squared equation. This time we're rotating about the line y equals -3. The x-axis tends to be the easiest for students to get. Everything else, all the other 5 scenarios that we are going to encounter, get a little trickier, okay? So I'm gonna draw the line y equals -3, that's here. So this is y equals -3, that's the thing we're now rotating it about, okay? As I said before, where do you put your pen pencil marker first? Where does that go when you're trying to figure out r out and r in? It doesn't go on the x-axis always. It goes on the thing that you're revolving it about, okay? So I'm going to put my marker here. Oh, first, I guess we should set up the bones of our equation. Like I said, we always should do first. So volume equals pi integral something squared minus something squared. The reason we always do this first is because it's easy to forget a squared, it's easy to forget a minus, it's easy to forget a parentheses, okay? The thing that goes on here are the bounds. We already found that those are 0 and 2. Okay, it is always this setup. I knew it was a dx because I'm rotating it this way. Okay, question?
Will the bounds like ever change in an FRQ or will they?
Yes,
okay.
but not by much. We're going to talk about. So the reason they could change is these bounds are with respect to what variable?
X, and it was like the Y.
Yep, so then we might have some other bounds over there. That's a very good question. Okay, we will have other bounds over there. Okay, so we're gonna put our pen pencil marker on the thing we're rotating it about, and to find my R out, which goes here, you're not gonna label this as R out in your FRQ, I'm only doing this for notes. Okay, you're gonna draw to the furthest away function. So the furthest away function in this case is still the 2x function. Here's where it gets tricky. Okay, give me your eyeballs, please. The distance from the x-axis to the green line, that distance is 2x. I am lengthening that by an additional how much? 3. So my full R out, that entire R out is what? 2x plus 3, or 3 plus 2x. It doesn't matter which place you put that 3, but it should make sense that I'm adding 3 to that entire value, right? I'm lengthening it by 3, okay? Then I'm going to put my marker, pen, pencil, whatever, on the thing I'm rotating it about and draw it to the closer function. The closer function is x squared. Again, you're not drawing it to the closer point. So some guys will be like, isn't the closer point 0? I don't care about the closer point, I care about the closer function because I'm drawing it for this whole thing. Does that make sense? So again, the distance from the x-axis to the blue line is how much? X squared, but my total R in is an additional how much? 3. So my R in here would be x squared plus 3. That would be my R in. Okay, questions on that? Let's do the next one. Again, we're going to draw our picture. The picture is super helpful. Usually on FRQ they give you a picture, which is nice, and you can draw all over that picture. That's totally fine. Okay, so we're going to draw my picture again. Again, I have this 2x and my x squared. I'll use some colors, green and blue. This one is 2x. This one is x squared. But this time I'm rotating it about the line y equals 7. That is above both of these. It doesn't matter if your graph is perfect, it just matters that it's either above or below. You'll never have to rotate it about something that cuts through the area. It'll always be above or below, or touching on the bottom or touching on the top, but it will never cut through the area. Does that make sense? Okay, all right, so bones of the equation, volume equals pi integral something squared minus something squared dx, because even though I'm revolving this one up, it's still going this way. Does that make sense? You have to think about that if I'm revolving it around dx or dy, okay? Or if I'm revolving it up or down or left or right, I guess I should say. Bounds are the same, so still 0 and 2 because we are still with respect to x, right? So my bounds are x equals 0 and x equals 2. Everybody get that and understand how those bounds make sense, okay? But I put my marker, pen, pencil, where? On 7, on the thing you're rotating it about. This one tends to be the trickiest for students, okay? I'm gonna draw to the farthest function away. The farthest function away is this one. This one is the trickiest for students. I wanna remind you something. The distance from the x-axis to the blue curve is how much? What's the difference from? It's x squared. That's this distance right here. This distance is x squared. You might draw that on your paper, okay? What's the distance from 7 to the x-axis? 7. So what would the purple be? 7 minus x squared, and it has to be in that order. It cannot be x squared minus 7. Has to be 7 minus x squared. Okay, total distance 7. This distance is x squared, so it's 7 minus x squared. Okay, now drawing to the closer function. So again, you put it on the thing you're rotating it about. Draw it to the closer function. Oops, Toshner, what are you doing? Okay, draw it to the closer function. So we're drawing it from here to the 2x. Now the total distance from here to here is how much? 2x. So that distance from here to here is 2x. The total distance from here to here is 7. What is the distance of my Rn? 7 minus 2x. Sometimes you will have to actually evaluate these, but the setup by itself is usually worth 2 points, sometimes 3 points just for the setup. Okay? So this setup is the most important thing. If you had to evaluate, you would like FOIL this, combine like terms, and then take the antiderivative, plug in all those bounds. Okay? Usually all that work is worth like another 1 point. Worth it to get another point if you can, but just be aware the most important points come from the setup. If you miss the setup, nothing else you do matters. Okay? Questions on this so far? All right, let's talk about what happens if we rotate it this way. Okay, you might stop and then start it again, and I'll just upload